Hello, in this video we'll go over this problem here. We'll try to solve it through three different techniques: nodal analysis, loop analysis, and superposition. I picked this problem because it has independent current sources, it has independent voltage sources, it has dependent voltage sources, it has dependent current sources. So we'll show that we're going to get the same answer through nodal analysis, loop analysis, and superposition. So we'll go over each one of these techniques. I recommend that you pause the video and give yourself 20 minutes to go over each one of these methods and then compare your answer to my answers and see whether you have the same answer I got for the output voltage V naught here. Okay, the first technique we're going to try is nodal analysis. So this problem has 1, 2, 3, 4, 5 nodes. We're going to take node number 5 as our ground. So we want to solve for V1, V2, V3, and V4. And remember, V1 is relative to ground, V3 is relative to ground, V4 relative to ground, and so on, V1 as well. So we have to take a look at each node and write KCL. If you go to node number 1, you'll see that you cannot write KCL. Why? Because between node number 1 and ground there is a voltage source. Its value is 9 volts, so we don't know what is the current going through this current source. So this is one of the special cases when we're handling nodal analysis. But luckily this voltage source here is not shared between two nodes, so it's just between V1 and the ground. So this means if this is 9 volts, this means that V1, this voltage here, is higher than that of ground by 9 volts. So V1 is 9 volts. So this is the equation we can get from this node. I don't really have to write KCL anymore if this V1 relative to ground is equal to 9 volts because of this voltage source. Now let's go to node number 2. For node number 2 and node number 3, you cannot write KCL either. Why? Because node number 2 you have a voltage source which is connecting it to node number 3. So you don't know what is the current flowing in this source. So I cannot write KCL here, I cannot write KCL here. When you see a voltage source that is shared between two nodes and there is no resistance in series, two internal nodes that is not one node and ground as the case here, then you have to think about the concept of the super node. So the first equation we can get from this part here is that V3 is higher than V2 by the value of this dependent voltage source, which is 2VA. Okay, so I can simply say V3 is equal to V2 plus 2VA. But you cannot, so this is the equation I mentioned here, but you cannot leave this equation that way. Why? Because VA is a controlling voltage. You have to write VA in terms of your unknowns. And my unknowns here are V1, V2, V3, and V4. So if you take a look here, you'll see that this is VA. It's between positive, negative. So it is equal to V2 minus V1. So I can get rid of VA here and write it as V2 minus V1 and reorganize. I obtain one equation between V1, V2, V1, V2, V3, and V4. So this is what I did here. So I wrote this equation. V3 is equal to V2 plus 2VA. And then I replaced VA, which is this voltage, by V2 minus V1. Then the equation I have V3 is equal to V2 plus 2 V2 minus V1. Okay. So I can reorganize this equation which I got here. I have to put them in order. I wrote them at V2, V3, and V4. Remember that I am not solving for V1 because I already know what is V1. So I'm going to get only 3 equations in 3 unknowns, V2, V3, and V4. And then every equation I'm going to write them in order. Okay, so the first equation I can get from this voltage source is that 3V2 minus V3 plus 0V4 is equal to 18. Now, I need to get a second equation because this voltage source stopped me from writing KCL here and writing KCL here. So I lost 2 pieces of information. I got one already. The second one you'll obtain, as we learned from class, is by forming a super node. You form one big node to enclose that source, and then you say the sum of all currents flowing out from this node is equal to 0. Okay, so I proceed here. I use this super node. The super node is here. Okay, so I enclose that voltage source which is connecting two internal nodes by this super node. So I'm going to say the sum of all currents flowing out from this super node is equal to zero. I have a one current, a second current, a third current, a fourth current, fifth current. So I have five currents. Let's write the expression for each one of them. This current here is 2 ampere. Okay, this current here is V3 minus V1 over 3, 2 plus 1. This current here flowing in the outward direction from right to left is V2 minus V1 over 8 ohm. This current here flowing from left to right is V2 minus V4 over 5 ohm. This current here flowing in the outward direction is minus 3 IB. And remember, IB is a controlling parameter. It is this current here. So I wrote these five currents, 1, 2, 3, 4, 5. And I have here minus 3 IB. But I cannot leave this equation this way. Why? Because IB is a controlling parameter. And as we agreed, whenever we have a dependent source, we have to replace the controlling parameter, which can be a voltage or a current, in terms of your unknowns. My unknowns here are V1, V2, V3, and V4. So what I did here, I said that this IB is the sum of this current plus this current using KCL. IB is equal to this current plus this current. This current is 2 ampere. This current is V3 minus V1 over 3. So this what I used here. I used this substitution. IB is equal to 2 plus V3 minus V1 over 3. So this current IB, which is a controlling current, is equal to this current, which is 2, plus this current, which is equal to V3 minus V1 over 3 ohm. So I took this and I substituted into this equation. I will obtain only one equation in V1, V2, V3, and V4. I'm going to write V1 as 9 volts, and I will simplify. I obtain this one here. I'm not showing the simplification steps. I suggest if you are not sure of what I've done, you pause the video right now, take a piece of paper and do these simplification steps. I did this in an external piece of paper, but I did not want to cram the slides with details. But I suggest that you pause the video now, start from this equation which has 5 terms, replace IB by 2 plus V3 minus V1 over 3, collect all the terms and keep them in order, V2, V3, and V4. You will obtain this equation here. Okay, we need to write one more equation for node 4. We wrote one equation here, V1 equal to 9. We got two equations from this source on the super node. And then V4, at node 4 there is no problem because it's connected only to a current source and resistances. So we can simply the sum of all currents flowing out from node 4 equal to 0. This is V4 over 2. This is V4 minus V2 over 5. And this one here as a current flowing out is minus 2. So V4 over 2 plus V4 minus V2 over 5 minus 2 is equal to 0. And this is what we have here. Reorganize, multiply both sides by 10, and collect the terms and put them in order. You obtain this equation here. There is no V3, so I included V3 with a 0 coefficient. I put this in a matrix form and I used MATLAB to solve it. I recommend that you do this solution using your calculator. Your calculator can solve a system of 3 by 3. Or you can do it using Gauss elimination or the method of determinants, whatever technique you feel comfortable with in solving a system of equations. If you do that, you'll obtain these three solutions, V2, V3, and V4. Remember, our target is to get V output, and V output here is V4. This is what we call V4. So V output is equal to V4, okay, which is equal to 4.8866 volts. Remember this number because we'll have to obtain it through two different methods. Okay, so this is the first part, doing the solution using nodal analysis. Now we move to do the second part, do the same solution using loop analysis. These are the currents I used. I feel a little bit comfortable using currents this way. Some people would like to use external currents. It's up to you. You can define this is one node, this is one loop, this is second loop. There are actually large number of ways you can select your 4 loops. I select the most obvious ones. We're gonna apply KVL around each loop. Okay, let's see. As we agreed in class, every loop that has a current source will create for us a problem in loop analysis because we don't know what is the voltage drop across that current source. For example, loop number 4, we have this current source here which is 2 ampere, but this branch is not shared between two loops. So if the current flowing here in this loop is I4 and this is 2 ampere, so I can immediately eliminate I4 and say I4 is equal to 2 ampere. So this is my first equation. Just by looking at the circuit, I say I don't really need to solve for I4. I know what's I4. Now let's talk about this loop and this loop here, loop number 1 and loop number 2. Again, I cannot write KVL here, I cannot write KVL here. Why? Because we have this dependent current source and we don't know what is the voltage drop across this dependent current source. But this current source can give us two equations. How? As we did in class, we can say if the current flowing here is I2, the current flowing here is I1, then this current, the current in this branch flowing from bottom to top is I2 minus I1. So I can simply say here that I can get one equation which is saying that I2 minus I1 is equal to 3IB. Okay? Sorry, this is I2 minus I1 is 3IB. This is correct. But I cannot leave this equation this way. Why? Because simply I have a current called IB. As we agreed in all the examples we have seen before, every time you see a controlling parameter, you have to replace it by your unknowns. So where's IB? This is IB. This is a controlling current, IB. What is IB in terms of the two currents I have? IB, as you can see here, is equal to 2 plus this current. Okay? So this current flowing in is equal to these two currents flowing out. This one is 2. This one is minus I3. So I can simply replace IB by 2 minus I3 in this equation. So I obtain this equation here. If you reorganize the terms, you obtain this second equation. So now we have two equations. I4 is equal to 2 ampere, and I have this equation here between I1, I2, and I3. I really do not have to solve for I4 anymore. Now, I got this equation from this current source, but I need a second equation. Why? Because this current source damaged for me two KVL equations in this loop and in this loop. As we agreed in class, whenever you see something like this, you build a super loop. So you bypass the current source by combining these two loops into one loop. We call it a super loop. So I'm gonna write now KVL around this loop here. So I'll go in the forward in the clockwise direction. So negative, positive, so plus 9 volts, positive, negative, minus 8, I1 minus I3. So this is the one I have here. Okay, let's continue. I'm continuing this way. This is I4, this is I2. If I assume the drop is positive, negative, then I'm going to see minus 5, I2 minus I4. Very important to understand how I got this one here. Okay, so what I did, I said I'm assuming that I2 is greater than I4. So if this is the case, then the drop I have across the 5 ohm resistor is with this polarity. If I2 is larger than I4, then the current is flowing from left to right. Then I have this polarity. Then the drop I'm seeing is minus 5 I2 minus I4. Okay? Very important to understand that. I'm going in the clockwise direction. Every time I see change from negative to positive, I count as positive. Every time I see change from positive to negative, I count as negative. I2 is flowing this way. Then it creates a drop positive, negative. I'm going in the clockwise direction. So this is going to be minus 2I2 is equal to 0. So now I went complete circle. Remember, there is no drop here in the bottom side. So I have this equation here. I simply reorganize it in the form of I1, I2, I3, and get rid of I4, replace I4 by 2 amperes. If you do that, and I encourage you again, if you're not sure how I got this, stop the video now and simplify this equation, collect the different coefficients, you will get this equation here. Okay, we have one more loop to do, loop number 3. Loop number 3 is a benign one. Why? Because you can see there are no current sources. I can apply KVL in the same way we learned in class. So I can simply say, I can go in the clockwise direction. I3 is flowing this way, so it creates drop positive, negative. So minus 1 I3, minus 2 I3, minus 2 VA, minus 8I3 minus I1 is equal to 0. So remember here, I assume that I3 is higher than I1. So this means they have polarity positive, negative. So if you go in the clockwise direction, you cross from positive to negative, then you have to include this drop with a negative sign as I've done here. Now, this one equation I have, but I cannot leave this equation this way. Why? Because in terms of VA, and VA is a controlling parameter. I have to write VA in terms of my unknowns. My unknowns in loop analysis are the currents. I1, I2, I3, and I4. So you can see this is VA. I1 is flowing from left to right here. I3 is flowing from right to left. So VA is nothing but 8 ohm multiplying I3 minus I1. Okay? So every time you see VA, you replace it by 8 I3 minus I1 because of the assumed polarity of VA. So I'm going to take this part here and substitute into this equation. I will reorganize the coefficients. I did that on an external piece of paper. I got this equation here. So now I have three equations and three unknowns, I1, I2, and I3. I know what's I4, it's 2 ampere. I don't have to solve for it. So using your calculator, you solve a system of three equations, three unknowns. Once you do that, you have your currents. Okay, I solved the currents. I got these numbers here. My target is to calculate V output. V output is a drop across the 2 ohm resistor, but this branch is not shared between second loop and any other loop. So the drop here, positive negative, is equal to 2I2. So if you take I2 here and to multiply it by 2, okay, you get 4.866 volts, which is exactly the same answer we got using nodal analysis. So the nice thing about our course 2CI5 is that you have actually many tools you can use to verify your answer. Usually you can apply superposition, use nodal analysis, loop analysis, Thevenin theorem, Norton theorem, use source transformation. We are going to hear more about this soon, but you will have many tools that you can use to verify your answer. So now we'll go to the last part, which is how to use superposition to do this calculation, how to get the voltage V output here using superposition. Okay, so superposition tells us if you have multiple sources, you will solve the circuit only for these sources one at a time, and then you remove all the other sources. You remove a current source by making it open circuit, you remove a voltage source by making it short circuit. But I'm warning you, this only applies to independent sources. These dependent sources here and here, they do not represent actual sources. They represent transistors, they represent diodes, and so on. They are not really actual sources. Okay, they are equivalent circuits of other components, so we don't consider them as independent. So superposition applies only to independent sources. So I have only here two independent sources, the 2 ampere current source and the 9 volts voltage source. So I'm gonna do now two simulations, not two simulations, two analyses. The first one, I'm gonna make this one open circuit, okay, and I will solve only for everything resulting from the 9 volts. And then I will make the 9 volts short circuit, and I will keep the current source, and I will solve for everything resulting from the current source. So let's see how this is gonna go. So in this slide, I made the current source open circuit. Okay, so this branch disappeared. It's not there because there is no current flowing in it. Okay, so this is how the circuit now looks like. I redrew the circuit again, and now I will have to solve it using any of the techniques I learned before. If I take a look at this circuit, I notice that I have actually two nodes only, V1 and V2, and this ground. Okay, so I can apply nodal analysis the easiest. Of course, I have here two nodes, but if you apply loop analysis, you have 1, 2, and 3. So here, loop analysis is actually harder than nodal analysis. So we need to apply KCL at node number 1 and node number 2. Okay, node number 1, I cannot apply KCL. Why? Because I have a voltage source connecting this node to ground, and there is no resistance in series. But because this is ground and this 9 volts, this voltage source is simply telling me that node number 1 has a higher potential than ground by 9 volts, that V1 is equal to 9 volts. Okay, so I managed to get one equation from that node. Now for the second equation, Can I apply KCL here? Someone will say, yeah, no, there is a voltage source connected here and I cannot apply it. No, you can apply KCL. Why? Because because of the change that happened in the topology of the circuit after we remove that branch, this voltage source has the resistance in series. Okay, so now you can apply KVL because the current flowing out in this branch in the outward direction from node 2 is equal to V2 plus this voltage source minus V1 divided by 3 ohm. So the voltage across these two resistances is nothing but V2 plus 2VA minus V1. I just want you to remember something very important, that V2 is between here and ground, and V1 is between here and ground. Okay, so this looks like a complete loop. So you go start the loop here, you go here, you go here, and then you go here. Okay, so if you apply KVL, you see that the voltage across these two is nothing but V2 plus 2VA minus V1. So I can write KCL here. So now let's write KCL. The sum of all currents flowing out is equal to 0. This current flowing to the left is V2 minus V1 over 8. This current flowing to the right is V2 over 7. Okay, so I have V2 over 7, V2 minus V1 over 8. This current flowing in the outward direction is minus 3IB. Remember, 3IB is flowing in, but I'm talking about currents flowing out, so I have to include the negative sign. This current here is flowing out, and I'm going to write it as V2 plus 2VA minus V1 divided by 3. Now, I cannot leave this equation this way. Why? Because I have the controlling parameter IB, I have the controlling parameter VA. I have to get rid of them. So how can we get rid of these currents? Let's see. Can I write IB? Yes, I can write IB. IB is equal to V2, is the current flowing in this branch. V2 plus 2VA minus V1 over 3. Okay, but what is VA? VA, as you can see, it is the voltage across this resistance, which is V2 minus V1. So you can write one equation in terms of V1, V2, and V3. So get rid of IB, write it as V2 plus 2VA minus V1 over 3, and then get rid of VA and write as V2 minus V1, and this is what I did here. Okay, so this IB in terms of V1, V2, and V3, and this is VA, which is this voltage here, is simply V2 minus V1. So take these two and substitute in this equation and organize. I'm not showing the organization step. You can do it in an external piece of paper. You will see that you will get the equation shown in the next slide. So I did the organization outside. I got this equation here, 15 over 8 V1 minus 97 over 56 V2 is equal to 0. Remember, I know V1. V1 is known. So I'm actually here not even solving 2 by 2. I'm solving actually 1 by 1 system. So if you substitute here for V1, put it as 9 volts and move to the other side and divide, you'll obtain this value for V2. Remember, this is V2 due to the voltage source. And V output, I can get V output from V2, because the same currents flowing into these two resistances, so I can apply the voltage divider concept. So I can simply say V output due to the voltage source is equal to 2 over 7 of V2. Remember, this is a voltage divider. Okay, so V2 between here and here is V output, sorry, between here and here is a fraction of V2 between here and here. Okay, so and this is what I said here. V output due to the first source, I call it V output 1, is equal to V2 multiplying by 2 over 2 plus 5. It's a voltage divider. You get 2.78348 volts. Now I have to repeat the problem again for superposition and find the output voltage due to the current source. Okay, so we're gonna do one more simulation, one more analysis after we remove this voltage source, so make it short circuit, and you bring back the current source again. Okay, so I went to the original circuit. I created a short circuit here, so this is gone. I restored the current source and its branch. Okay, and now I'm all set to calculate the output voltage. So I will redraw the circuit. I just want to bring your attention to something. Because I now connected this point to ground, This 8 ohm, is now in parallel with this current source because they share the start point and they share the end point. This is all one point. And also this 3 ohm is now connected between this node and it goes all the way to ground. Okay, remember this is ground here now because of this short circuit. So I'm gonna redraw the circuit. I will make this 8 ohm in parallel with the source, and I will make this 3 ohm connected between this node and ground. Okay, so this is really how the circuit looks like. The 8 ohm is connected in parallel with the current source, the dependent current source, and the 3 ohm is connected between this node and ground. Okay, my target is find V output, which I'm gonna call here V3. I use the nodal analysis again. I call this one V1, this V2, and this V3. Okay, so now we start to apply nodal analysis. Can I apply KCL here? No, I can't. Why? Because between node 1 and node 2, there is a voltage source with no resistance. But I can get from this voltage source two equations. The first equation is that V2 is equal to V1 plus 2VA. But what is VA here? What is VA here? VA is the voltage between this node and ground. Okay, remember VA was the voltage across the 8 ohm resistor if you check in one of the previous slides, and the 8 ohm now has moved its other side to ground, so this is VA. So VA here is nothing but V1 in this circuit. See, this is V1, is the voltage of this point relative to ground, and this now VA. So I wrote that V2 is equal to V1 plus 2VA, and I'm going to replace VA by VA is equal to V1. So you get that V2 is equal to 3V1, or if you organize it in the form of an equation, order the equation V1, V2, and V3 and put 0 for the coefficient V3, obtain this equation. As we agreed in previous examples, whenever you have a voltage source connecting two nodes, you build a super node around it and you sum the currents flowing out. How many currents are flowing out? 1, 2, 3, 4, and 5. We have 5 currents. This one is 2 ampere, this is fine. This one is between V2 and ground, so this is V2 over 3. This current flowing out is V1 minus V3 over 5. This current flowing out is minus 3IB because 3IB is flowing in. This current flowing out is V1 over 8. So I wrote all these 5 currents here, okay? Of course, I cannot leave it that way because I have IB, I have to get rid of IB. This is IB. IB, as you can see, is equal to 2 plus V2 over 3. You have to write IB in terms of your unknowns. And your unknowns here are the nodal voltages. So this current is flowing in, according to KCL, current flowing in is equal to sum of the two currents flowing out. So IB is equal to 2 plus V2 over 3. So this is what I did here. And you substitute in this equation and you reorganize. And again, I'm not showing the organizational steps. I recommend you stop the video for a second, take a piece of paper, make the substitution from here into this equation, and collect all the coefficients in order. You will get this equation here. 13 over 40 V1 minus 2 over 3 V2 minus 1 over 5 V3 is equal to 4. Okay, we have only one equation, one nodal equation to apply. We at this node 3. Node 3 is a benign node. Why? Because it's connected to a current source and resistances. So if we say the sum of the currents flowing out of node 3 are equal to 0, then we have V3 over 2 plus V3 minus V1 over 5 minus 2 is equal to 0. This is what we have here. Multiply by 10 and reorganize, you obtain this equation here. Okay. Now you have 3 equations, 3 unknowns, V1, V2, and V3. You solve them, you obtain the voltages. These voltages are due to the current source alone, okay, because we remove the effect of the voltage source. If you solve for these voltages, this is what you get: V1, V2, and V3. But the output voltage if you check in the previous slide, the output voltage is nothing but V3. We call it V output 2 because it is the output voltage due to the current source. It's 2.1031. So now the total output voltage using the concept of superposition, it is the output voltage due to the voltage source, 9 volts voltage source, and the output voltage due to the current source. We calculated this one earlier. Now we calculated this one is 2.1031. We sum them. You obtain this number. Remember, we did not keep infinite precision as we went through that. So this becomes 4.88658, which is really can be rounded to 4.8866 volts, which is the same answer we got using loop analysis and nodal analysis. So whatever technique you should use, the circuits we're handling give you a unique solution. There is always one set of currents flowing in the branches and specific set of voltages for the given ground. Okay, so hopefully this example, which was solved in 3 different ways, will help you understand more how to apply nodal analysis, loop analysis, and superposition.